Welcome back, students. Now let us see properties of nucleus. Because already we are learning about the nuclear physics. Nuclear physics is the branch of physics which deals about constituents and properties of nucleus. Constituents mean the protons, neutrons and electrons. And let us see now properties of nucleus. What property nucleus has exist. Let us see one by one. The first property of nucleus is nuclear charge. Nuclear charge. Nuclear charge. Inside the nucleus, what components are there? Protons and neutrons are components of the nucleus. And proton has the charge 1.6 into 10 raised to minus 19 coulomb, and mass can be represented 1.674 into 10 raised to minus 27 kg. So, inside the nucleus, proton has the charge, but a neutron is a chargeless particle. Already we know. Then, how to represent nuclear charge? Nuclear charge is the number of protons present inside the nucleus. So, generally, see here, Q equal to, how to represent? Q equal to Z into E. What is Z? Number of protons present inside the nucleus. And what is E? Charge of electron. What is the charge of electron? Charge of electron equal to 1.6 into 10 raised to minus 19 coulomb. So, the total charge of the nucleus can be represented E is equal to Z into E. Where Z represents number of protons, E represents magnitude of charge. That is magnitude of charge of the proton. Next property is nuclear mass or mass of nucleus. Nuclear mass. Nuclear mass. Inside the nucleus, protons and neutrons are there. So, the sum of the masses of protons and sum of the masses of neutrons, that we are calling nuclear mass here. Directly, the mass of the nucleus can be represented mass of proton, mass of proton, mass of proton plus mass of neutron, mass of neutron. Then, how to represent mass of the proton? Mass of the proton can be represented number of protons into mass of proton. Number of protons into mass of proton plus mass of neutron. How to represent neutron? Neutron can be represented A minus Z. Already we know in the last video. Into what? Into mass of neutron. This is what? Nuclear mass. That is the sum of the masses of protons and neutrons in the nucleus. That we are calling nuclear mass. We know that. What is the mass of the proton? Mass of the proton equal to 1.6726 into how much? 10 raised to 27 kg. Right? Z is atomic number. A minus Z is number of neutrons. Then what is Mn? Mn represents mass of neutron. How much it is? 1.6748 into 10 raised to minus 27 kg. If you want to in terms of atomic mass unit, then you can represent, doesn't matter. Simply, the nuclear mass is the sum of the protons and neutrons present inside the nucleus. That we are calling nuclear mass. Next property of nucleus. Properties of nucleus. Nuclear size. Nuclear size. Nuclear size. Students, from Rutherford alpha ray scattering experiment, it is found that atom is spherical in nature and the size of the nucleus is very smaller of the order Fermi. I mean of the order 10 raised to minus 50 meter is the size of the nucleus. Experimentally it is clear that if a number of protons and neutrons are increased, then volume of the nucleus is increased. Directly, Experimentally it is found that the volume of the nucleus is directly proportional to mass number. I mean, how much protons and neutrons are increased inside the nucleus, that much volumes are increased. Right? And nucleus is assumed to be spherical or spherical. Volume of spherical. How much volume of spherical? That is 4 by 3. 4 by 3 phi r. That is volume directly proportional to mass number. Here 4 by 3 and phi are the constant. What is the variable? R. R represents radius of the nucleus. Then from this relation what you are taking? The radius of the nucleus directly proportional to mass number of nucleus. Or radius is directly proportional to a raised to 1 by 3. Or radius of the nucleus must be equal to some constant. Some constant R0 into a raised to 1 by 3. Well, constant we are calling empirical constant. This empirical constant is always constant and average value can be taken. Average value can be taken R0 equal to 1.2 into 10 raised to minus 15 meter. Then from this relation what you are taking? The radius of the nucleus is directly proportional to cube root of mass number. That is R directly proportional to a raised to 1 by 3. This is what? The nuclear size. I mean, the size of the nucleus depends on how many protons and neutrons are present inside the nucleus. That relation can be taken R equal to R0 raised to 1 by 3. Right? This is what? Size of the nucleus. Next one we have to see density of nucleus. Density of nucleus. Density of nucleus. We know density. Density means mass by volume. Density means mass by volume. Here nuclear density. Nuclear density can be represent mass of the nucleus divided by volume of the nucleus. See here. How to represent? Density equal to mass divided by volume. Mass divided by volume. Here mass means mass of the nucleus. And we represent volume of the nucleus. Here how to represent mass of the nucleus? Mass of the nucleus can be represented mass of a nucleon into mass number. How to represent? If small m represent mass of a nucleon, then A represent mass number. This is what mass of a nucleus. Small m represent mass of a nucleon. A represent mass number divided by volume. Volume is how much? Volume is assumed to be spherical. Spherical can be taken how much it is? 4 by 3 pi r cube. Right? But you know what relation? R equal to R0 raised to 1 by 3. Right around. Then how to represent this value? Rho equal to density of the nucleus. 3 goes upside. What you will take? 3 m into A divided by 4 phi. What is R? R0 raised to 1 by 3. R cube. How to represent R cube? From this equation, how much it is? R0 cube into A, because R equal to R0 raised to 1 by 3, then R cube means how much? R0 cube into A. From this, what are taken? Mass number get cancelled. Right? Then what is density? Density equal to what? 3m into divided by 4 phi into how much? That is R0 cube. How much it is? R0 cube. What is m? Mass of a nucleon. What is the mass of the nucleon? Mass of the nucleon is 1.67 into 10 raised to minus 27 kg. That is 1 AMU. Then what is R0? R0 is constant. How much it is? 1.2 into 10 raised to how much? Minus 15 meter. By putting m and R0 value, because 3 is constant, 4 is constant, 5 is constant. Putting m equal to this value and R0 equal to this value, you will get rho equal to 2 point something into 10 raised to 17 kg per meter cube. per meter cube. Students, this is the density of the nucleus. What is the density of the nucleus? 2.3 into 10 raised to 17 kg per meter cube. Look at this equation. This equation indicates density of the nucleus not depends on number of protons, number of neutrons or electrons directly. Density of the nucleus is independent on mass number. Independent on mass number. For all nucleus, density must be constant. That value is of the order 10 raised to 17 kg per meter cube. 10 raised to 17 kg per meter cube. What these are? These are represent properties of nucleus. One is nuclear charge, nuclear mass, nuclear size and density of the nucleus. But experimentation is found that the masses of the nucleons always greater than actual mass of the nucleus. I mean, if we weigh the total nucleus and if we remove the nucleons from the nucleus, then you weigh, it is clear that the masses of the nucleons always greater than actual mass of the nucleus. Right? Then here we have to introduce the one more term that we are calling mass defect. Let us see concept of mass defect. Mass defect. Right. Let us see the concept of mass defect. Concept of mass defect. Represent by delta. Mass defect. What we said? If we compare the nucleons, if we compare the nucleus, the mass of the nucleons always greater than actual mass of the nucleus. First of all, let us see. So I will take this atom. So here it is the nucleus. The whole mass of the atom supposed to be concentrated at some region that we are calling nucleus. Right? Inside the nucleus, what components are there? Inside the nucleus, protons are available and neutrons are available. And here electron is revolving like this in circular orbit. What are the nucleons? The sum of the masses of protons and neutrons, or protons and neutrons together called as nucleons. If we weigh this total atom, if we weigh the total nucleus and if we weigh the separate nucleons, always masses of the nucleons always greater than actual mass of the nucleus. The difference in masses of nucleons and actual mass of the nucleus, that is represented in terms of mass defect. What is mass defect here? Mass defect is the difference in masses of nucleons and actual mass of the nucleus. See here. Actually, how to represent masses of the nucleons? Masses of nucleons is the sum of the protons and neutrons. What are the masses of the nucleons? Z into mp. What it is? Mass of the proton. Then A minus Z into m and represent masses of neutrons. Then what is the masses of nucleons? Masses of nucleons. Let us take capital M represent actual mass of the nucleus. Actual mass of the nucleus. This actual mass always less than nucleons mass. What I said the mass defect? Mass defect is represented by del N. What is the mass defect? The difference in masses of nucleons and actual mass of nucleus. That we are calling mass defect. What is the mass defect? Difference in masses of nucleons. Difference in masses of nucleons. Difference in masses of nucleons and actual mass of nucleus. This we are calling mass defect. Generally, this mass defect is represented in terms of atomic mass unit because nuclear mass is very smaller as compared to kilogram. That's why this mass defect, it is represented in terms of atomic mass unit. Atomic mass unit. After this, we need to study the one more physical quantity that is very important regarding the nucleus. That we are calling binding energy. Binding energy. Binding energy. See here. Inside the nucleus, the protons and neutrons are holding by very strong force that we are calling nuclear force. The nuclear force we will study in the next video. Let us see what is binding energy here. See here, binding energy is the minimum energy required to separate the nucleons from the nucleus. What is binding energy? The average energy or minimum energy required to separate the nucleons from the nucleus. That we are calling binding energy. Or this binding energy can be defined alternative manner also. Binding energy is the energy with which nucleons hold together inside the nucleus. The energy with which nucleons hold together inside the nucleus, that we are calling binding energy, or the minimum energy required to separate the nucleons from the nucleus, that we are calling binding energy. How to define? The minimum energy required. Minimum energy required. Minimum energy required. Minimum energy required to remove nucleons from the nucleus. Nucleons from the nucleus. From the nucleus, or the energy with which nucleons hold together inside the nucleus, that we are calling binding energy. This binding energy can be represented by one more equation, that is Einstein mass energy relation. Using Einstein mass energy relation, E is equal to mc square. Here m represents mass defect. Del m into c square. What is del m? Mass defect. What is mass defect? Zmp, that is mass of proton plus mass of neutron minus actual mass of nucleus. Actual mass of nucleus. Then how to represent this binding energy formula? Binding energy can be represented del m equal to Z into mp plus how much? A minus Z into mn minus of what value? Del m. Right? What this is? Mass defect into how much? C square. This is what? Binding energy formula. I mean, if we give this much of energy to nucleus, nucleons are separated from the nucleus. Here Z represents atomic number of the nucleus, mp represents mass of the proton, A represents mass number, Z represents atomic number, mn represents mass of proton, mp represents mass of neutron, mp represents mass of the proton, and capital M represents actual mass of the nucleus. Then what is C? C represents speed of the light. C represents speed of the light. But here we have to define one more term, specific binding energy or binding energy per nucleon. Specific binding energy or binding energy per nucleon. Specific binding energy. Specific binding energy. Binding energy or binding energy per nucleon. Binding energy per binding energy per nucleon. You can call specific binding energy or binding energy per nucleon. Binding energy per nucleon. Binding energy per nucleon. See here. How to define specific binding energy here? Specific binding energy is the energy required to separate a nucleon from the nucleus to an infinite distance. What it is? The energy required to remove a nucleon from the nucleus to infinite distance. That we are calling binding energy, specific binding energy or binding energy per nucleon. Directly, the binding energy per nucleon is the binding energy divided by mass number. How to represent specific binding energy? The specific binding energy is binding energy of the nucleus divided by mass number. I define two ways. What are they? Specific binding energy or binding energy per nucleon is the minimum energy required to separate a nucleon to an infinite distance. I mean, if the energy required to separate a proton and neutron from the nucleus and bring to an infinite distance, or directly, the binding energy divided by mass number of the nucleus. Binding energy divided by mass number of the nucleus. That we can represent specific binding energy or binding energy per nucleon. See, what is binding energy? This is the binding energy formula directly. How it is? Specific binding energy can be represented. Binding energy is formula. How much it is? Z into mp plus how much? A minus Z into mn. Minus of how much? Actual mass into c square. This represents binding energy divided by mass number. That is the ratio of binding energy to mass number we are calling the specific binding energy or energy required to separate a nucleon from the nucleus to a infinite distance. That we are calling specific binding energy. But significance of specific binding energy is specific binding energy or binding energy per nucleon indicates the stability of nucleus. This term indicates stability of the nucleus. Now we have to see the graph of specific binding energy versus mass number. That we will see in the next video.